My research project topic is concerning fungal growth on commonly used modern engineered or composite wood materials in the non-museum environment, and specifically how the interaction of these two might be of concern to the conservation community. So this project was undertaken as a preliminary observational study examining the environmental parameters of mold growth, as well as the fungal resistance of two specific composite wood materials. The two materials chosen for the study were OSB, or oriented strand board, also known as sterling board, and WBP, or weather and boil proof board, which is also known as marine plywood. The study was conducted over a period of 42 days with data collected every 7-day period. Controlled relative humidity chambers were used with 2 equal-sized samples of each type of wood in each chamber, providing 6 surfaces for examination for a total of 60 unique surfaces, including the control samples. Cycling moisture was added to the sequestering containers themselves, replicating one of the main culprits encouraging fungal growth in the heritage environment, which is moisture as a result of condensation. A visual mold growth index model was used as the primary system of measurement and comparison over the course of the study. So this study was inspired first by a visit to a rather unique non-museum environment, which was the former home of self-taught artist Jerry Dalton, known affectionately as Jerry's Pompeii. Jerry resided in the Maida Hill area of West London until his death in 2019. An assessment of the property containing a large quantity of Jerry's work made with a wide range of found and commercially purchased materials was done by the second-year sea glass conservation students, overseen by Jennifer Dinsmore in February 2020. The problem with such spaces as artist homes, studios, and workshops are similar to many of the environmental control issues encountered within the non-museum heritage environment and often seen within historic homes. As they're not purpose-built to sustain a collection, storage, and a large influx of visitors, controlling the environment is challenging, particularly in the case of relative humidity, which is a significant environmental factor in mold growth. The use of modern composite materials at Jerry's inspired the examination of engineered wood materials in this study, as they are ubiquitous in both the museum and non-museum environment. They're used for display, storage, shipping, and in modern artworks themselves. So the main objective of the study was to, 1, better understand the environmental parameters favorable to mold growth. Number 2, to better understand fungal resistance of the materials ubiquitous to the modern built environment. And 3, to provide data for future research into the environmental conditions most favorable to mold growth and preventive strategies which might help non-museums such as historic properties, artist studios, and workshops. So the experiments were set using commercially purchased samples of 18mm thick OSB and WBP board, cut uniformly to sizes of 18mm by 25mm. The samples were inoculated with mold spores by exposure to the common residential studio environment for a period of 14 days. Each humidity chamber, as seen in the image on the right, contained 2 smaller sequestering containers holding each of the samples, as well as digital hygrometers and Boveda 2-way relative humidity exchange packets calibrated to the correct RH levels, with the exception of chamber D, which required a much higher RH level and where a soluble salt solution containing potassium sulfide at a concentration of 12% weight volume was used. Originally used in cigar humidors, Boveda packets contain saturated salt solutions within a water vapor permeable reverse osmosis membrane, providing a consistent RH range over a period of from 2 to 6 months with no need to top up. 1.5 milliliters of water was introduced to the side of each sequestering container every 14 days using a pipette to replicate cycling condensation patterns. Several models have been developed in the identification and categorization of fungal species. Such models developed include the transient biohydrothermal model, which takes into account all potential environmental influences on spore germination, and also the isopleth system, which concerns itself mainly with predicting either germination time or growth rate. A visual index for identifying the presence of fungal growth on surfaces was chosen for this study as the standard of rating and categorizing the level of fungal growth observed visually and microscopically. As outlined in the index at the top of the slide, each degree of visible surface growth is given a number rating, which provides a visual reference for evaluating the degree of fungal activity. The system is useful and straightforward as the numbered rating system allows for quick interpretation, which can be graphed and requires only reflected light and digital microscope if available. However, its drawbacks as a rating system include the differing opinions, potentially leading to confusion as it tends to be entirely dependent on personal visual interpretation by the conservator. Finally, the weekly data was recorded using digital microscopy. A Dynolite basic model in the bottom right corner of the slide was used, and 10 times, 50 times, and 200 times magnification were applied. The observations of each sample were limited to once per week, as in preliminary RH experiments conducted prior to the study. It was found that more movement of the samples disrupted the life cycle of the fruiting bodies, skewing future mold growth and results. I'll now give an overview of some of the results that were found within each chamber, touching only briefly on the lower humidity chambers, as these showed very little difference from week 1 to week 6 of the experiment. So here we have images of the samples contained in chamber A with an RH range of 62% plus minus 3% on day 42 of the study. No significant changes were observed from week 1. However, WBB sample A, seen in the bottom row, showed small localized areas of subhyphal growth on day 1, only visible under 200 times magnification. This reveals that at one time between manufacturing and point of sale, the wood was contaminated with fungal spores, and the correct conditions were present to promote initial mold growth. These growth patterns did not progress during the 6 weeks under conditions of 62% RH, even with the addition of moisture. Similarly, chamber B, with an RH range of 74% plus minus 3%, saw no significant changes over the course of the study. No presence of spores, hyphal growth, or conidial heads which were observed. This somewhat contradicts the assertion within some of the literature, which indicates that upwards of 70% RH is a dangerous range for objects environmentally. However, it has been documented that mold has grown within heritage properties at an even lower RH than 70%. This finding supports the assertion that RH is only one significant factor and others must be present in order for mold to grow. The most significant changes were seen as expected within the higher RH chambers, which reached between 80% and 95% RH. All samples within this range saw significant growth on all surfaces. Chamber C, with a range of 84% plus minus 3%, saw accelerated growth from day 7 with visible hazing over the surface using no magnification, localized areas of thick concentrated growth, and defined conidial heads, particularly on the cut edge surfaces by day 14. The cut edge surfaces of OSB sample C on day 14, seen at 50 times and 200 times magnification, shows 2 variations of growth, with the defined conidial heads of the body appearing as brush-like structures upon thin stalks projected off of the surface. Both blue and black versions can be seen here. The growth pattern, shape, and color of these conidial heads appear consistent with Aspergillus, which is one of the 5 most commonly observed species in the heritage environment. Similarly, you can see here on the opposite side cut edge of surface of OSB sample C on the same day, clearly defined growth in the form of bright blue conidial heads containing spores emerging from the surface on thin stalks. Under reflected light with no magnification, these appear as thick suede-like growths over localized areas of the surface. The WBP sample from chamber C also experienced an accelerated growth pattern after day 14 of the study. It's significant to note that the growths themselves were markedly different from those observed on the OSB samples, specifically in how they seemed to spread horizontally over the surface rather than the long, tall, defined stalk seen in the OSB samples. This indicates a different species which has an inclination towards deeper subhyphal growth. Finally, chamber D, with the highest RH range of 90% plus minus 3%, also saw dramatic results in growth. Notably, trends began to emerge in the growth patterns with certain areas appearing preferential over others for the mold. The cut edge surfaces were the most vulnerable, supporting both fungal growth and pest colonies. Similar to OSB sample C, we see here conidial heads on thin hyphal stems consistent with the species Aspergillus. The extremely high RH appears to have accelerated growth and surface area coverage. Examination of samples in the high humidity chambers on day 21 of the experiments saw a marked increase in microbiological activity, as well as pest activity. The active presence of transparent mites, not visible to the naked eye, were observed under 50 and 200 times magnification. Consultation with Jim Hardy, the Director of Science at the Royal Entomological Society, confirmed that these were a classification of Acari, most likely a mite. While the subspecies of mite was not able to be confirmed, some were able to be ruled out, such as book lice, for instance. Both samples, OSB and WBP, within the high humidity chambers experienced some degree of infestation from the 21st day of the experiment onwards. The OSB sample from chamber C, day 35, was chosen to highlight here, as it exhibited the most representative sample of mites at every stage of the life cycle. In these images, we can see mites at the larval, proto-nymph, and adult phases. It's important to note here that the presence of these pests did affect the rate of mold growth. This was particularly observed on sample C, as by day 21 of the study, almost all mold growth had been consumed by the colony, which were actively observed from day 21 onwards. Their frass, appearing as black dots over the sample surface, provided good indication of their presence, and it quickly multiplied over the course of the study. And finally, here we see the WBP sample from chamber D. The trend of thick, low-growing species of mold of a green-gray color growing over the cut-edge surface. Interestingly, again, we see further evidence that the cut-edge surfaces were preferred by several species of mold. Additionally, the colonies of mites favored these areas, particularly areas that were porous, as they seemed to provide ample shelter, and multiple Acari could be seen teeming within these cavities at one time. The data obtained from the observations over the 6-week study were able to be assigned numbers in correspondence with the mold growth index rating system, based upon observation using no magnification, as well as 50 times and 200 times magnification. These graphs were created. The most striking trend immediately evident is the lack of any movement at all within chambers A and B throughout the study. While it's notable that WBP sample A had some evidence of previous growth at a range of 60 to 75% RH alone, seemed not to be a significant enough factor to promote mold growth. Another notable trend is the tendency for various factors to affect a direct upward trajectory of mold growth, even in the higher humidity environments. The OSB sample from chamber C experienced a marked decrease in growth at week 3, primarily due to the presence of mite colonies. However, the cycle of growth began again and was further promoted by the presence of the frass left by the mites. Finally, as evidenced by the introduction of small quantities of water at regular intervals to the sides of the sequestering containers outlined in the experiment settings, the effect of both RH and surface water activity in tandem appeared to accelerate the process of growth. The most compelling example of this phenomenon is the growth progression experienced by sample C, WBP, on week 6. Unexpectedly, after very little change within the first 35 days of the experiment, with the final addition of water deposited onto the side of the container, a critical threshold was reached wherein germination was possible. This provided further evidence that spores can lay dormant on the surface until ideal conditions for germination are met. So the aim of the study was to better understand the fungal resistance of 2 commercially available engineered wood materials at varying levels of RH with the addition of cycling moisture. The objective being to provide further data to assist in the mitigation of these environmental factors within the non-museum heritage environment. The information gathered during the 6-week study found consistency with the literature regarding the general range of RH which is acceptable, which is generally below 70% RH, and even found resistance within these 2 engineered wood materials up to an RH of 85%. However, it was also observed that several other crucial factors can accelerate the propagation of mold. Most relevantly to this study was the addition of cycling surface moisture. This recreation of a common occurrence of condensation in uncontrolled environments such as historic homes, studios, churches, and storage facilities was found to be an equal, if not more significant factor in the development of mold growth. This is particularly important to note in the care of historic properties in the UK, where the annual average precipitation is nearly 1/3 of the calendar year, with an average RH in the Greater London area alone being greater than 75%. Significantly, it was also found that commercially available wood, while treated during manufacturing to produce the most unfavorable surface for fungal growth, cannot definitively assert fungal resistance, as fungal spores are ubiquitous in the outdoor, residential, and even museum environments. Therefore, it must be taken on by the conservator themselves to recognize early warning signs of contamination, diligently treat these surfaces, and monitor the environment in which they are displayed and stored. Several future avenues of research to explore include further analysis using methods such as FTIR to determine the composition of glues and additives, expanding the number of materials tested, such as medium density fiberboard, for instance, and the number of samples tested. And finally, to expand the environmental parameters to include factors such as ventilation and wetting and drying cycles. And thank you very much for your attention.
Thank you. Any questions?
Cody, that was really interesting. Thank you very much. I'm intrigued by the mites that you saw. Were they present before you exposed the samples to RH? Did you, when you looked at the samples at the beginning, do you think there were mites there, or?
So no, in the preliminary examination of the samples before they were put into place in the RH chambers, there was no sign of the mites. And as the mite colonies expanded, the presence of the black, what I could probably posit as frass over the surface, multiplied from week to week, until by the end there were quite highly concentrated areas of frass. So that's one sort of early indicator that there are mites present, and you can actually there are actually guanine tests that you can do in vacuuming up some of that frass and using analytical methods to then determine the concentration of mites present. And that's one way you can help to prevent the sort of further propagation of those colonies. But yeah, there was no sign of mites on any of the surfaces that were examined before placing them in the RH chambers.
But so presumably they were there, eggs were present, if your containers were airtight.
Yeah.
Do you think then they have a role in terms of mold control if you observe them?
There is actually, interestingly, there is actually some literature about using mites it's actually used more in agriculture, but I did see some potential for that. But then I think obviously there are some problems. There are some problems with introducing mites into the into the historic environment. It would obviously have to be done in a very controlled way, I would think. But it was really interesting because they did consume the majority of the fungal growth that was there, but then it did propagate again. So it wasn't as though they had clearly consumed all of the dormant spores that were there. They sort of they did their job in a way. But the environments that mites like, fungus likes as well. So it was kind of interesting to see them sort of thrive together, and in that way. Interesting.
Yeah, very interesting. Thank you. Thank you very much.
Can I also ask a question?
Hi, Johannes. Yeah.
Hello, Cody. Really cool, very interesting. I like the pictures as well.
Thanks.
I was just wondering, I know it's not really, it wasn't maybe the focus of the study. I was just wondering if you came across, so one thing is the RH, right? So that's kind of very important for the growth. Is there any way to control or to mitigate growth apart from controlling the RH when you cannot control the RH? is there anything like treatment-wise or like coatings or whatever you can do to mitigate that?
Yeah, actually, I think that RH plays a role for sure, but as like a lot of the literature sort of covers, there are a bunch of factors that need to be in place in order for mold to grow anyway. So RH on its own typically is not regarded as the only thing that's needed for it to grow, first of all. And then I sort of elaborate on it a little bit more in the paper, but the best way to actually mitigate for it is to recognize the early signs of it, so that things like vacuuming the surfaces, like very simple things, can be put into place by, you know, these sort of methods of cleaning surfaces before they come into the environment, and knowing what you're looking for. Because I found that dino light was actually a really useful tool in seeing things you couldn't necessarily see with the naked eye. You could see a little bit of hazing over the surface maybe, and then you would look at it with the dino light and see, you know, very obvious hyphal growth. But if you didn't know what you were looking for, perhaps you would miss that. And I found that that in itself would be a really useful tool, just to be able to, you know, caring for the surface before it gets placed into the environment, so that it doesn't become a problem. Does that make sense?
Yeah.
Okay.
Cody, I may have missed it, but did you say what temperature you did your experiments at? I'm just curious.
Yeah, the temperature, I didn't, yeah, you're right, I didn't mention that. I mentioned it in the paper. It was a residential sort of, I had to set up a studio at home, a home laboratory. And so the temperature was very steady at between 20 to 22 degrees. It didn't, it was monitored sort of daily, and it never really went too far above or below that. Kathleen, you have your microphone on.
Thank you, Cody.
Hi.
Okay. Does anyone else have any questions?
Hello, hello.
No, I took my off. Turn off my.
Hey, I had a question, if that's okay.
Hello.
Hi, my name's Alex. Ex-City and Guild student. I'm now at the British Museum. I was really interested to see.
The cheap one. This is yours.
Sorry, Alex. Just one second. Kathleen. Okay, sorry, Alex, go ahead.
Listen, it's absolutely fine. You're doing really, really well. So my question was, I really liked the graph where suddenly there wasn't much activity and suddenly there was loads of activity.
Yeah.
And I wondered if you could talk a little bit more, because that seems quite an extreme change, and I wanted to talk a little bit more about that. I was also interested.
Yeah. So
the follow-up question was also just, if I was interested in
What it is, discussion book.
It sounded like you were suggesting that there was a point that was reached, and I was interested in how long you thought anecdotally it would take if you removed the moisture for that to not be an issue anymore.
Okay, so I think I understand what you're asking. Sorry, I missed the beginning of that part, the question. So what you're asking is why there was such a dramatic spike at that one time with that particular sample of wood, right? So it was hard. It was kind of hard for me to understand that, because it happened at day 35, and after a consistent addition of cycling moisture to the sequestering containers, which were not applied directly to the samples. They were applied to the side. It was sort of more to replicate, dripping condensation. And what I understood from the literature was that basically, mold spores will remain dormant until the conditions are basically present for them to propagate. And so from that 7-day period, what I understood to have happened was that basically something about that final addition of moisture pushed it over the edge and it somehow there was an explosion of growth. And so I think that was the best I could do to explain it at the time, because really it was just a strange progression, and it was in a higher humidity chamber, so you really would have expected it to. That was one of the things I found striking, is that it doesn't tend to just go up and up and up and up. It goes like up and then down and then up again. And I feel like if I had continued the experiment, you would continue to see that, because mold sort of propagates more mold with, you know, how it works. So yeah.
And then the follow-up question was just around, like anecdotally, I don't know if you had any idea, but like the interesting thing then is if you remove the moisture, what do you think the graph would have done, I guess?
What would you see? Yeah. I suspect that if, I think like there's a lot of really interesting room for further studies on this, because I think what I sort of established from this was that that there was actually because of the free and bound water and wood anyways, and then the addition of moisture, that's actually a possibly equal, if not sometimes more significant factor than the RH itself. Like it being held in the high RH chamber was, you know, important, but I think that I wonder if no moisture had been included at all, if we would have seen any results. And I think if I were going to redo it, I would have another chamber where no moisture is included, at perhaps a higher RH, and maybe another one where there's a slightly lower RH, and compare those two as well. That would be another interesting sort of parallel study to do. Yeah.
Thank you so much, Cody.
Thanks, Alex. Anyone else have any questions?
If there is any question, thank you so much, Cody.